Hello. So we had seen yesterday, or we had seen in the last lecture, I should say, that the limitations, the advantages of Gibbs phase rule. Today we will learn just now the limitations of Gibbs phase rule. In any system that includes two phases or more, there must be an equilibrium between the phases. So the very first point is that in Gibbs phase rule we had seen that the process has to be reversible and it has to have an equilibrium. So if there is no equilibrium, that means Gibbs phase rule will not hold. Next, a non-equilibrium between the phase of the system cannot be considered by Gibbs phase rule. Okay, so if there is no reversible process, if there is no equilibrium between the phases, then we cannot apply Gibbs phase rule. Then the third limitation is equilibrium of solid phase systems, that is when the solid is present in finely divided state, cannot be explained by this rule. There are certain limitations, that is the system then shows deviations under different conditions. What are they? We will see later. Next, the most important limitation: if equilibrium between the phases is not defined by a single constant, temperature and pressure values, then the Gibbs phase rule will not hold for that system. Now, in thermodynamics, we mostly consider the fluid systems, the systems in the gas phase. Gas is also a fluid, it can flow. Now, recall, thermodynamics deals with conversion of heat to other forms of energy. So, then where have we learnt about this? We are still to begin. First and foremost, we have to learn that heat is not a state function. It is a path function. In other words, it is not a state variable. It is a path variable. Now, the next question that follows is, what is a variable? What is a path variable? Let's see. A state variable is the property that describes a system in a particular state. A path variable will be a property of the system? No, it is a property of how the system moves from one state to another. That is the path of the state, the path of the system, the path by which a system moves from one state to another. State variables indicate the initial and the final state only. If any two of the state variables are known for any condition of the state, that is initial state or the final state, then the other properties can be easily found out by calculations. Example, in the ideal gas equation you have got PV is equal to nRT. If we know either PV or TV or NP, we can find the other variables. That's what we learned also in Gibbs phase rule. But look at the path variables. In path variables, in thermodynamics, there are basically two path variables, namely heat and work. Are heat and work properties of any system? Let's see. Consider a man lifting up a heavy box. He is applying all his might, that is a force, to displace the box from its position on the ground to some distance above the ground. Here you see, the box is here. See the man's posture. He has already spread out his legs. He is trying to pick up the box. The box is heavy, and up there the box goes, right up from the ground level to the upper position. There is transfer of energy from the man to the box, and it has been displaced from the ground to a height above the ground. So we say the box has done some work. What is work now? You know, in physics, work is equal to force into displacement. So W is equal to force into displacement. That means work is proportional to the distance moved by the system, that is the box. In our case, does it depend on the path traveled by the box to move from the initial state to the final state? Yes, it is. Supposing the man lifted up the box in one step to say a height just 1 feet above the ground, 1 foot above the ground. Then next he lifts it 2 feet above the ground. Again, he lifts it 3 feet above the ground, but every time he is changing the position. Then we say that the work is done in 3 different steps in 3 different ways. So, work is proportional to the displacement, as here we see in the previous slide I showed you that it has already moved from the initial step on the ground to the final step on top, where the man is holding a few feet above the ground. Therefore, work is not a state property, it is a path function, it is a path variable. If you change the path, if instead of the man standing there and doing the work, he starts changing his position, then the path also changes of lifting the box from that particular position to another position. What about heat? In case of heat, we are studying the interconversions of heat to other forms. Is that a state property? Is that a state function? We are aware that heat is equal to the thermal energy, and that energy is a property of the system. Thermal energy is a property of the system, right? But not heat. Then what are we saying? Heat is not a property of a state property? Wait, let us see. Energy of a system doesn't just comprise of the thermal energy. It comprises everything. That is, it comprises the internal energy from potential energy, kinetic energy, atomic energy, molecular energy, everything whatever is intrinsic, that is inherent in that body. So, energy is a property of the system, but heat is not. Why? Because heat is transferred to a system from the surrounding, or it can be generated within the system by some process. Now again, when it is generated by some process, then it can have different paths. That is, it can be generated by different chemical reactions. For example, say we are having our cells, that is the living being. In our body, different reactions are taking place, and from there different amounts of heat is getting generated in our body. Again, when we feel too hot, we sit under the fan. We want to give out the excess heat outside to the surrounding. Again, from the surrounding, the heat is coming to our body. So, heat transfers by radiation, convection or conduction, as you have learnt in your elementary classes, and that is why heat is not an intrinsic property of a system. It is a path function. It depends on the path. It is called the path variable. So then, is there something called extrinsic property? Yeah, there is. What is intrinsic property and what is extrinsic property? Intrinsic properties are those which are inherent in the system. They depend mostly on the chemical composition, the structure, the arrangement of the constituent particles in the system. For example, density. But extrinsic properties are those which are not inherent in the system. They are not inborn, they are not inside the system. It depends on the color of the system, size of the system, length of the system, and so on. Example, weight. Weight changes according to the position on the surface of the earth. So, these are extrinsic properties. That is, you can say color is also an extrinsic property. If you start painting the surface of a substance, you will say the color has changed. Well, that's fine. So, extrinsic properties are not inherent in the system. Now, not to confuse between intensive and extrinsic properties, which we learned very early in the study of thermodynamics. What are intensive properties? They are independent of the mass of the system. But intrinsic properties are within the system. They are inherent. They are there associated with every part and particle of the system. Extrinsic properties are not inherent in the system. They come from outside. If a system does work, then that work is an extrinsic property. If a system gains heat, heat is an extrinsic property. If a system is becoming color, then that color is due to its absorption of light, and so again it's an extrinsic property. It is not inside that system. What is an extensive property then? An extensive property depends on the extent of the system, that is mass. So simple. Mass depends upon the quantity of matter, and that is extensive. It is also there inside the property. So you will say intensive and extensive are both intrinsic? Yeah, you are right. If you say that, you are right. Intrinsic properties include extrinsic properties as well as intrinsic properties. But extrinsic properties are those which change, and they are not there inside the system. They change due to the system exchanging something with the surrounding, or the surrounding exchanging some matter or something with the system. For example, I told you weight. Mass is an intrinsic property, mass is an extensive property, not intensive, but it is weight which is extrinsic property because it changes with the gravity of the earth. I hope you got it. With this, you have finished the basic introduction of thermodynamics, and now we will see how we can use heat to convert to work, and in case of fluid systems we will mostly deal with pressure volume work. So we will have to first prove that pressure volume work is equal to force into displacement, which we will learn in our next lecture.